Hello friends, welcome back to my channel, Physicist, Buddhist in California. So today I'm going to talk in detail about a book that I mentioned in one of my previous videos briefly. So this is the book Quantum Field Theory and Critical Phenomenon, 4th edition by this famous physicist Zinn. So I have the book's cover here, hopefully you can see it properly. So this is a classic book in its field, and this book deals with two of the most important phenomenon in quantum field theory, the renormalization group and the use of renormalization group to study critical phenomena. So in this book the author starts with the fundamental definition of quantum field theory in terms of path integral, which is the standard definition, and of course the path integrals are then solved in terms of Feynman diagrams. The author lays the foundation. He first describes what a quantum field theory is, how is it set up in terms of a path integral which is infinite dimensional, and then how to solve or how to approximate, because there is no way to really solve this. It's insoluble exactly, but it can be approximated using Feynman diagram method up to 1 or 2 Feynman loops. So he starts with a basic foundation, basic definition of quantum field theory. He sets up the path integral method both in Minkowski space and in Euclidean space, which is very useful also for the finite temperature investigation of quantum field theory. And of course it has direct relevance to statistical mechanics. So this book is unique in that sense that it covers the renormalization group and its application to study critical phenomena, not just in particle physics but also in statistical physics and magnetism, for example, in condensed matter physics. So that's what this book is about. It's a very long book. It's a very detailed and dense book. Of course, it's a book of quantum field theory. It's not an easy book to read, but if you want to get a good understanding of quantum field theory, how to actually set up a problem in a quantum field theory language and how to solve that problem in terms of Feynman diagrams, starting with the path integral formulation of a quantum field theory. And he does this for lots of good examples in two-dimensional, where one space dimension and one time dimension, and then he also covers in the normal space-time dimensions, which is 3 space dimensions and 1 time dimension. So the standard problem that one starts with in the study of quantum field theory is the is the scalar model. So interacting scalar quantum field, where you have it's also called a phi-4 theory, where you have the scalar field represented by the Greek symbol phi, and phi-4 is that you're taking the self interaction of 4 scalar fields with each other. So starting with a neutral scalar field with a non-zero mass. So this is a massive scalar field and it's neutral, so there is no gauge degree of freedom in the beginning. And then he moves to the abelian gauge quantum field theory, where the scalar field is no longer neutral. It carries a charge and it carries an abelian gauge, and the same process is repeated. All the steps are gone through, and how to solve this problem, how to approximate this problem using Feynman diagrams is then explained. And so once you set up the problem, and then you can calculate you can actually calculate the renormalization group flow of the theory, where you take the gauge coupling, for example, Of course, the renormalization group can also be applied to the mass, and of course it involves the field itself, because the field itself gets rescaled by the quantum corrections. But the most important quantity is the Gauss coupling. So you start with the setting up of the equations of renormalization group for the Gauss coupling, both for the scalar field and then later on for the abelian Gauss, and then for the non-abelian Gauss also. So abelian Gauss is the U1 Gauss, which is the standard Gauss in one of the most famous quantum field theories, quantum electrodynamics, and non-abelian Gauss, which is SU2 or SU3, which is the used in other famous quantum field theories. For example, the weak nuclear force is described by an SU2 Gauss quantum field theory, and the strong force is described using an SU3 Gauss quantum field theory. And based on their Gauss freedom, these theories have very different behavior as the energy scale is changed in the renormalization group flow. So for example, in case of abelian Gauss, it is expected that the Gauss coupling should increase with the increasing energy, where for the non-abelian Gauss field theories for SU2 and SU3, the Gauss coupling declines or decreases as the energy increases. This author, after going through these well-known problems in quantum field theory, in particle physics, now so far I have discussed the application of quantum field theory, especially the renormalization group, in particle physics, where one studies these scalar quantum field theory, and first we study it Gauss independent, which is neutral scalar field theory, and then we give it a charge, and then we move on to the abelian Gauss quantum field theory and non-abelian Gauss quantum field theory, and study the renormalization group flow of these quantum field theories in 3+1 dimensions, which is the space-time of the universe in which we live. Now, the quantum field theory arose in that context back in the 1920s, and when it was first proposed by Heisenberg and Pauli and Jordan and Bohm, the same people who laid the foundation of quantum physics. They also were the first to study quantum field theory, but they could not solve the problem, because when they introduced the interactions where the quantum fields are actually interacting, for example in quantum electrodynamics, the quantum field of the electron is interacting with the quantum field of the electromagnetic field, which manifests itself as a photon. So when those interactions were put in place, it turned out that the theory was plagued by infinities, or the theory was sick, and this sickness could not be resolved at the time. It took 20 years, and shortly after World War II, thanks to the work of these really brilliant physicists, most important of them being Richard Feynman and Julian Schwinger, two very important, very famous American physicists, and one Japanese physicist, Shin Ichiro Tominaga, who all three independently managed to resolve the issue of removing the singularities and make the theory finite in the limit of infinite energy. So once that problem was resolved, that opened the door in few years later to study the renormalization group flow of these theories, and so that basically was put in place by 1970 by another great American theoretical physicist, Kenneth Wilson. So that whole renormalization group program allows one to study the behavior of the theory at different energy scales. Okay, so of course at lower energy scales, where we actually make all the measurements, and it also allows us to see whether the theory is finite at high energy, which is known as ultraviolet limit. So the key to obtain a renormalization group flow of a theory is its renormalizability. So if the theory is renormalizable, which means that it yields a finite answer when the energy is taken to the infinite limit, which is basically the limit one has to take in particle physics, then you can do a renormalization group flow of that theory also. So this was how the quantum field theory and the renormalization program arose in physics back in the 1940s. So by late 40s, this program was completed successfully. And like I mentioned earlier, that program was then extended to the renormalization group, which is basically where you take the theory and you study how the gaze coupling or the other physical quantities like the mass or the fields themselves behave under a change of scale. So if we let the scale, because renormalization group itself is basically you solve the problem by fixing the value of the physical constant, say the mass of the electron. In case of quantum electrodynamics, the mass of an electron or the charge of an electron is basically taken to be the measured value at some value of energy, let's say 1 million electron volts, and you basically substitute that in the equation. So this is the process by which the renormalization program is carried out. It's a very fairly complicated program, but that's how it's done. But in renormalization group, the energy scale is basically it basically extends from the infrared low energy scale to high energy scale, the UV scale. Okay. So that program was completed by the late 60s. In between, in the 1950s, people decided that there is another whole field of physics where quantum field theory could be applied, and that is the statistical physics or the condensed matter physics. So you can use quantum field theory to also understand the behavior of a magnet or a metal. Okay, but the thing is that condensed matter exists only at very low energies. So unlike the particle physics where the energies are relativistic, the energies in condensed matter or statistical physics are distinctly non-relativistic. So they had to figure out how to extend the theory from the relativistic domain to non-relativistic domain, and this was successfully completed in 1950s. And so the renormalization program was also successfully completed, and there of course nature thankfully provides a cutoff. In case of particle physics, there is the only cutoff nature provides is the infinite energy, because a particle is understood to be a point particle. So in quantum field theory, a particle's fundamental definition is it's an quantized excitation of a quantum field, and it cannot have any structure in it. So it's a point part, which means it has zero dimension, which means that you have to make sure that the theory provides consistent results from zero energy to infinite energy. But in case of condensed matter physics, the things are not quite so complicated, because let's say you're studying a magnet on a lattice. So a lattice is a mathematical construct. It's the distance between the nearest neighbor atoms on in a solid. So it's usually on the order of a few angstrom. So you can use the lattice constant in condensed matter physics as a natural cutoff. So you don't need to push the theory all the way to zero energy. To infinite energy. You can use the size of the lattice itself as to impose a limit on the quantum field theory that you're setting up. So this program was completed in 1950s, like I mentioned earlier, and there also the renormalization. So once the theory was renormalized, which means that you can take the next step and you can study the renormalization group. Okay, so you can do renormalization group only for renormalizable quantum field theory. So if the theory is not renormalizable, then you can't do the renormalization group flow of the theory. So that's what was done, and so there what happens that the renormalization group of a quantum field theory in a condensed matter physics allows you to study what's known as the critical phenomenon in condensed matter physics. Critical phenomenon is basically a phenomenon where the system exhibits similar kind of behavior on all scales. Okay, so for example, one very good example is boiling water. So once you take a pot of water and you start boiling it, and eventually when it gets close to the boiling temperature, you'll see that it's filled with bubbles. It turns out these bubbles at the boiling point exist from all the way from the size of the water molecule to macroscopic dimensions, like up to a centimeter, which you can clearly see with your eyes. So the water at this point, it's standing at a critical point where the boundary between the liquid and the gas has disappeared. So it is both at the at the same time. And this phenomenon is scale invariant, that from the molecular level to the macroscopic level, like I said, up to a centimeter or 2 centimeters, you can see the bubbles of diameter of 2 centimeters. The same phenomenon exhibit itself. So it's very important and very interesting phenomenon for physicists to study. And to study this phenomenon, quantum field theories come in very handy. And this is how a quantum field theory's renormalization group then plays a very important role. That if you look into the renormalization group flow of a quantum field theory for a condensed matter system, then if and this is known as by the mathematical function called beta function. So beta function is basically, for example, for the coupling constant, it is basically giving you the behavior of the coupling constant on several different energy scales. So if at any point the beta function goes to 0, okay, so beta function basically is it's represented as the gradient of the coupling constant with respect to energy. So if the gradient or the derivative is 0, then that's a fixed point in the theory. So in case of renormalization group, that fixed point becomes the critical point meaning it is scale invariant, and at that point theory reveals a very rich array of phenomena, okay, and it can be elevated from a quantum field theory to another theory called conformal field theory, which is basically a quantum field theory with added degrees of freedom. For example, this scale invariance that I said. So if you have a quantum field theory that's also scale invariant, then it can be extended to this conformal field theory, which has much higher symmetries than a quantum field theory. So this book actually covers all of that, except it doesn't cover the conformal field theory, but he does cover like all the other parts that I've talked about. So to recap, what does this book covers? It teaches you how to define a quantum field theory in terms of path integral, and then how to solve that path integral approximately using Feynman diagrams. It shows you how to do that for particle physics, by taking examples of scalar quantum field theory, and which is gaze invariant, which could be gaze invariant, or could have abelian gaze or non-abelian gaze, and then how to set up renormalization group flow of this quantum field theory, which is shown to be renormalizable. And then he, in the last part of the book, he extends now from relativistic quantum field theory to non-relativistic quantum field theory. Particle physics is all relativistic quantum field theory. So condensed matter physics, the statistical physics, is non-relativistic quantum field theory. And he shows how to set up the path integral, how to solve the path integral in terms of Feynman diagrams, and to study the critical phenomenon that one is interested in. And so this is all covered in this massive book. You can see it's more than 1,000 pages long, and it is one of the classic books in its field. And so that brings me to the end of my lecture. I hope you enjoyed listening to me, and was entertaining and informative for you, and I hope to see you again in my future lectures. Thank you for your time.